My name is Martin Spencer. I'm going to give you a little bit of a background about me. Obviously, I'm not from around here originally, as you can probably tell. I was born in England. I've always been an aviation geek, I'll say that now. I love everything to do with aircraft. My dad used to take me to air displays back in the day and saw some very fine aircraft back in the airport in Birmingham where I was born. Dragon Rapids and all Viscounts were flying for domestic, for BEA and Aer Lingus. I remember seeing those. So that got me really in tune with aircraft. And I've been a geek since then, I guess. So when I left high school, I went down and worked for what was the original de Havilland company. Became Hawker Siddeley at that point, where the tiger moths, all the moths were designed. The mosquito was designed out of there, and then we had the obviously the heron, the doves, and then the tridents were the final. And the Comet was obviously also designed there. So I had a pretty good, in my opinion, I was very proud and happy to work did an apprenticeship there. I learned a lot of good things. I also got a degree in aero engineering at the local university, and stayed there for a couple of years working as a designer on the flight deck of what was the 146 at that point. Left there and went to work for a helicopter company, Bristow Helicopters, and I'd always been interested in helicopters, but and I know there was some discussion on helicopters earlier. After one flight out to the North Sea in a Wessex, which was a Westland, or the what's that, 55, I think? No, S61. Decided helicopters were not for me. I was just anyway. I still like helicopters, but I sort of swayed away from that. Then I worked for an airline in England, Britannia Airways, and this is where I got indoctrinated into the Boeing way, because Britannia was the first operator of the Boeing 737-200s in the UK. We had 30 on our fleet. And so I got to know the Boeing way, the Boeing materials, US materials, US fasteners, and they were also the first operator of the 767 way back when they were first introduced. And I got the opportunity to come over to Seattle on training for the 67, and that's what got me here. I came and saw Seattle, and I had a buddy that was working at Boeing, and he showed me around the local area, and he had his license, so we flew down to St. Helens. And so anyway, I decided this is a good place to at least, transition. So we had two small kids at that point, two and four. And we decided to give it a shot and come over here. And so we gave it a 5-year plan, and I'm still here 33 years later. So obviously the plan. So that was back in 1987, came over here, and I worked for a company called Heath Techna, and they were based in Kent at that time. That was their headquarters, and obviously composite interiors was what they did, was their mainstay. They were doing a lot of retrofits, replacing the old open hat rats on 707, 737s with enclosed bins. And so we worked down there, and then one of the things that Heath Techna did in that area in Kent was that they were under what they call the Boeing umbrella. And if Boeing added an extra buck to their pay rate, then everyone went over to Boeing in Renton. And so they wanted to get away from that problem. And so they decided to look at another facility that was way away from Boeing. And they ended up in Bellingham, and they built a facility back in 1990 up on Woburn Street in Bellingham, and moved their headquarters, for the interiors anyway, to Bellingham, and they became part of Hexcel, which obviously we have an Hexcel around the corner here. They became part of Ciba Geigy at one point, and they've had a multitude, and ended up being a Safran company. I stayed there quite a few years. I was an engineering manager on the interiors, but decided I wanted to try it on my own. So I left them 21 years ago and formed my own company. At that time, I'd got involved with in flammability, and I became a DER, which I still am a DER, and was signing off their test plans, reports, witnessing tests for their interiors, and decided I wanted to expand it and do a better job on my own. So I became a consultant, and then in traveling around and seeing different pieces of equipment, test equipment that was in use, decided I can do a much better job in making those, my engineering background. So we set about developing our own set of equipment based on the FAA requirements that were published in their fire test handbook. We made, in my opinion, a much better mousetrap. And it's come around. 21 years, we've become the top seller of FAA-approved test equipment in the world. We have customers all over Asia, all over Europe. Boeing and Airbus are both our customers, as well as all the other major interior manufacturers and seat manufacturers as well. And that's basically what I'm going to be talking about today is what we do to certify the interior of an aircraft from a flammability perspective. The last thing is I am the president of the EA 404 chapter up in Linden. And I know we had someone mention about the fuel. So currently Linden fuel is $5.15 a gallon. So if anyone wants to, I know you have to fly up there to come back, but still, it's the cheapest, I think, in the state at the moment. They just announced that reduction, so that's a good thing. Two other quick things before I move on. I also started 4 years ago an association called Whatcom Young Aviators. And we got 30 kids, middle and high school kids, and we teach them everything about aircraft, aviation, sorry, not just aircraft. We try and get them involved. We do almost like a ground school when we meet, teach them navigation, how a plane flies, all the aspects in ground school at a lower level. I have an Allegiant captain who's my instructor, and he does a great job. And then we have another guy we actually have 2 planes in our semi-hangar. We had a hangar at the airport, but when COVID hit, the port didn't want us to not pay our rent, and we said, we haven't got any kids, we can't. So we moved to my facility, and we actually have 2 planes in there. I have an Osprey, which I own, which was in rebuild. The Osprey is a wooden amphibian with a motor on the top. And then we also have a Zenith 650 wings and tail that was donated to us by some of the EA members in Linden. We haven't really started that, but that's for the kids to get some hands-on experience as well. So we're trying to cover both the hands-on. We have a flight simulator for the kids to use. It's all free for the kids, anyone in Whatcom. Anyway, so and we are starting that up again in a few weeks. We're now back in the process of getting those kids involved again. And the last thing I want to just mention before we start is a new exciting thing that I'm involved with, which my wife thinks I'm crazy, which is fine, is we've just announced a new airline up in Bellingham called Marlin Air, and keeping the same names. And we're going to fly out of Bellingham with Embraer 140 regional jets to Spokane, Portland, Pasco, and Boise. Because, put them on the list. Anyway, there's definitely missing a service to get from this area, and obviously you're not very far from Bellingham, so it'll provide an opportunity to get over to Spokane, over to the east side, Portland, and so on. So anyway, that's coming. We formed the airline in December. We've been working with the FAA for the last 8 months, and we've passed the first gate. We're working with the DOT to get our approval that side. We hope to be operational by August, September this year. It's not going to happen that quick, but there's a lot of things we have to do. We have a director of operations, chief pilot, and a director of maintenance. So anyway, if anyone wants information, it's Marlin Air. We have a website, we have a Facebook page, and we're looking for input back from people, the places they want to fly.
Is that M-A-R-L-I-N or
yes.
M-A-R-T-I-N?
L-I-N. So the Marlin comes from Martin, and Lindsay's my wife, and we talked about that. So she's part of, that's why it's Marlin Engineering and all the Marlin side of things here. So Marlin Air. Anyway, that's it. That's my opening spiel. Now we're going to talk about aircraft flammability, and it will be based more towards the commercial side, but it applies to Part 23 aircraft too. My DER ticket allows me to approve both Part 25, which is the commercial aircraft, and Part 23, the small aircraft. And although I don't do as much, I am actually working on a project now. Anyway, let's move on. So, just want to get this thing to work. Okay. So, fire worthiness it's been a big focus for the FAA. Obviously, there's been accidents over the years you've seen, and we're trying to make sure that the aircraft is as fireproof as possible. There's in Atlantic City, on the East Coast in New Jersey, at the airport there, they have the fire test group works there. That's where they develop tests. They do a lot of research on what can happen in an aircraft. They have a DC-10 and a 707 that they can set fire to and look at what happens inside the aircraft. So they've got all the tools there, and they are the prime people that everyone goes to when it comes to aircraft flammability. They're known worldwide, and they're always working on new things to develop new rules and improve the safety even further. We want the interior materials to prevent and slow down the spread of in-flight fires. So there's two scenarios we look at. In-flight fires and then post-crash fires, as we call them, which is what we saw recently. It's very apt, seen the A350 recently. And we'll talk more about the types of tests we do and why we do them during part of the presentation. This is just a very brief background. Oh, by the way, I'm going to send this whole presentation to Larry, and you can download it. It's got videos in it, so it's not something I'm just sending it by email, but you'll be able to download and look at this in the future as well. Okay. This just gives a brief timeline as to how different tests came into play over the last, 50 years. There hasn't been a major new test come out since 2003, although we're working on some new ones now, which we'll talk about briefly. A bit small, but you can see a timeline as to a lot of the new rules came in because of accidents. It was a very much not in front, but it was always, an accident happened, what happened, why did people perish, and how can we make this better? So we're trying to be more proactive now in looking ahead and seeing what could happen and determine the tests that are required. Currently we're in the process, or the FAA is in the process of trying to simplify the whole, and we're talking to Part 25, Part 23 is a little different, but we're talking about this threat-based analysis. In-flight, interior accessible. So that means anything that when you're in a seat, you can see the sidewalls, the bins, the ceilings, the bulkheads, the seats themselves, the carpet. That's an in-flight accessible fire. So if there's a fire becomes apparent, there's an extinguisher, you can extinguish it. Interior non-accessible. This is an area that we've really been trying to work on to make even more flame retardant. We're talking now areas above the ceiling that you can't see, areas below the floor. Inaccessible areas, so if a fire occurs, you don't either know about it or it's hard to fight that fire. So we've now upped all the regulations for those areas, and we'll talk about an accident that really pushed that to make those materials in that area very fire hard. And then we talked about the post-crash, where the plane is, if there's a fuel fire outside, it's going to burn, but we want to offer the passengers more time to escape so they're not damaged or they're not impacted by the fire immediately. We want to get people off the plane, and we've just seen a very good example of that. We're still working on that. It's very close to being released, so I think he said due completion 2023. It's going to be this year for sure. We're that close to getting all that new all pulled together. I say questions. Anyone got any questions on that first bit? Oh my God. Go ahead.
Well, you talk about making interior portions of the plane, both the ones you can see when you're sitting there and the ones you can't see above and below the floor. But what about all that baggage?
In the cargo or in the overhead?
Baggage in the cargo, or in overhead too. You can't control that.
You can't. But you want to make those bins so that it'll contain a fire if there is something up there. I mean, the materials that we use are very fire hard, and I'll explain how that's changed over the years. But yeah, we have no control over what people bring on, other than they shouldn't really be bringing on anything. Hopefully TSA's caught any bombs or anything like that. But
regular carpet bags,
yeah,
they burn up.
They would, yeah, because they're not fire retardant. Yeah, that's true.
So the two planes that they're used for the test bed are aluminum skinned. Is the new composite aircraft pose different challenges for the?
Sure does, and the FAA has really worked hard on trying to make sure that that fuselage will prevent fire from entering into the cabin. That was a big thing they worked on, and we're just about to release more tests for components that are made of composite materials that are secondary structure inside the fuselage.
So is there a test lab for composite fuselages yet, or no?
They've got large sections of fuselages in Atlantic City that they did tests on. They use a huge oil burner to actually try and penetrate that material, and so yeah, they've definitely done all the tests on that. We know you can't stop the plane from burning. It would be impossible to try and build a plane that would never catch fire. So that we have to accept that, but we try and provide a barrier. So if there's a fire outside, it's not going to penetrate. As we've seen in that A350 accident, the plane's going to burn up, and it's not the fact that it's graphite, carbon fiber material. That's not going to burn. It's the resins that are used to bind it all together. And traditionally, the resin for the fuselage would be an epoxy-based resin, which is going to burn eventually. I mean, we made a change, and let's talk about that when I get into the interiors. But yeah, the resin is the culprit in all this, and the interiors use a different resin system that was developed back in the 80s to overcome some of the problems from an accident. We'll talk about that. Any other questions on the open? Right. Okay. So on the passenger aircraft, we have these areas. We've got ducting and insulation up in the overhead. Wiring is up there. In the interior, we have large surfaces that we have to look at separately. So all the sidewalls, the ceilings, the bins, the bulkheads, lavatory walls. We want to make sure when they burn, they don't emit a lot of heat that would create a hostile environment in the cabin. So those materials are very low heat release. Thermoplastic parts get different tests, like the trim on the seats, the plastic parts, gap covers between bins, normally thermoplastic materials, elastomers, the rubbers, the seals, they have a different test. Everything gets tested. Nothing on the aircraft would never get on the aircraft unless it's tested in some fashion. Seat cushions, the backs and the bottoms, they are tested in a totally different test. I have a good video of how that's tested. The floors themselves are tested to flammability. The carpet is tested. Cargo linings, obviously that's an area where you don't want, if you have a fire, you don't want that penetrating. And there was an accident that showed that very tragically and changed the rules on cargo liners inside those. So they're very, very strictly controlled as far as the test. Anyway, that just gives an overview of the interior and how we test and some of the tests we do. The very basic test we started with was the Bunsen burner, and it's just a standard Bunsen burner you see in a chemistry lab when you were at school. Temperature is about 1700 degrees Fahrenheit, and the original tests were just horizontal tests, and you apply a flame for 15 seconds, pull it away, and then watch the burn rate as the flame progresses down. And there was limits set to say if it stays within 10 inches a minute, then we're okay. But that was considered a pretty strict test back in the day, back in the 40s, obviously. Flame propagation. It was felt that the more stringent test was to actually put the test samples vertically and apply it to the surface. And so we added the 12-second test. It means the flames applied for 12 seconds, taken away. The material has to self-extinguish within 15 seconds on an average of 3. The burn length cannot exceed 8 inches. And the drips have to self-extinguish if there's any drips from material. A second test was added in the 70s to further increase big panels. So the 60-second test means the flame's there for a lot longer. And it's a more severe test. So all of the interior components have to meet this test for sure.
Are you testing just test cards, or are you having to test actual parts in it?
So at the end of the day, we certify the aircraft interior. So we don't test materials unless they're only used like a trim strip, for example. We'd only test that. But when it comes to a honeycomb panel that's on a bin door, for example, we test the completed final assembly. And if it's thick enough, we'd set the Bunsen burner on both sides of that. So we're measuring, we don't measure up through the core, but it's the surface that's going to burn. And it be the fiberglass skins, it'll have either a paint surface or a decorative applied surface. And that's what we're looking to stop burning. Okay? So yeah, it's the final assembly. So we certify the parts that go into the aircraft. And as it's installed, where it's installed, how big it is, also plays a part as to how we test the materials. So in '84, the seat all burn test was added to simulate a fire inside the cabin after a post-crash. The materials themselves had to meet the basic interior test of a Bunsen burner, but once you ever start introducing this external fire, you want to make sure that if the fire does get into the aircraft through an opening, a door, or a window, that the fire does not spread across the cushions, which was evident in one of the accidents we will talk about. So this test was developed, as you can see, it looks like a seat frame. We have a horizontal and a vertical cushion that sits on there that simulates the buildup of a cushion with a dress cover on, and if necessary, a fire blocking layer between the cushion and the dress cover. What you see there is a kerosene burner that we build. That's pretty intense. I got a video of that actually in operation, which we'll see later. But that was the test. That's the test that we do to all seat cushions. If they change the material of the cushion, the foam, the dress cover, we have to retest that configuration to make sure any configuration on the aircraft is covered, be it leather or a pseudo leather material or a fabric. They're the main materials that are used. Since this first got introduced, the foam manufacturers have now upped the foam and make very good fire retardant foams. Before they were just polyurethane, and we had to cover them with a Kevlar cover, which was very uncomfortable, added a lot of weight to the aircraft. So now the manufacturers have come with fire retardant foams. It's just the foam and the dress cover. So this is the cargo oil burner. Was introduced in '86. Class C compartments are the ones that you can't access during flight, and so we don't count the freighters. Cargo aircraft. This is a passenger cabin aircraft that has the baggage bays below the floor. Once again, it's the same burner that we just saw, but it's mounted vertically, and there's a burn-through requirement. It looks like that's actually failed, but it's just the flames. We're looking for burn-through on the center of the panel, and that's a typical panel that's used in the cargo bay. It's normally like a 50, 60 thou resin material that acts as a very good barrier. That's a 5-minute test, and a 2-minute test that we have to set that with no penetration. And the materials that are mounted in the ceiling of the cargo bay have to meet a much higher, because the flames are always going to go up. The bottom, the floor, and the sides only have to meet a less stringent requirement, but the ceiling of the cargo bays have to meet this full force of this burner. Heat release added in '86. Excuse me. It's called the OSU heat release test because it was developed jointly with Ohio State University, Boeing, Airbus, the FAA, and EASA. Or it wasn't EASA then. It was before EASA was involved. Jointly got together and developed this test method. They felt that if they can suppress the amount of heat that's being given out when an aircraft interior is on fire, then it provides more of a safeguard for the passengers. So they came up with this test to test the peak heat release in a 5-minute test, and also the amount of heat in that first 2 minutes is given off. And they're requirements that were set, and we have to meet those. And I have some examples of that test. Smoke density. So in addition to the heat, we want to make sure that the materials used in the cabin have very low smoke emissions. There was an accident where we used old epoxy adhesives. The smoke was so thick people couldn't get off the plane. They couldn't see. The only way is on the floor to get under the smoke layer. So they adopted higher requirements for the amount of smoke that's being generated by any of these materials on the interior of the aircraft. Yes?
Are you testing for toxic volatiles too?
So, Good question. So it's not an FAA requirement. The FAA does not consider the toxicity as a major contributor to a death on an evacuation. Airbus and Boeing have their own internal toxicity requirements, which are required to be met for their materials for new aircraft. So yeah, there are some toxicity. At the end of the smoke test, if there's a toxicity test required, then before we open the door and evacuate the box, we will extract some of that gas and run it through different apparatus to test for mainly hydrogen fluoride, hydrogen chloride, hydrogen cyanide, sulfur dioxide. I guess that's it. And CO, carbon monoxide. So there is tests, but the FAA we're not required by the FAA to do those tests. It's an internal thing with the manufacturers. But yeah, yes.
What sets the criteria? I mean, it seems kind of arbitrary, 4 minutes or 60 seconds.
So what happened is they used the data they got from burning an actual aircraft. They had monitors in there, and they can determine what the life expectancy in a certain temperature. They did do toxicity at that time, looking at the smoke and how much heat was generated. So all that data determined on a large-scale aircraft test, they pared it down to what we can test on a desktop or in a fairly small scale test. So the data that was determined was based on survivability in a large scale.
They set an airplane on fire or something?
Oh yes. Yeah, they have a fuselage, like I said, a wide body and a narrow body in their hangar at Atlantic City Airport, and they've set fire to the outside with a pool fire. They open doors, and they instrument what happens to the seats, to the interior. They have an interior in there. And this was years ago. I mean, that test is not necessarily done so often now, but in the early days, they did a lot of instrumentation to determine what the life expectancy was in certain parts of the aircraft based on this criteria. So that's how these numbers came about. It wasn't just picking out the air. There was some reason behind it. Yeah. Yes.
When they were doing this testing, did they do anything to simulate the actual conditions the aircraft would be in during this plane, like at 5,000 feet going 400 miles an hour?
So these tests here are purely post-crash. If there's an in-flight fire, you want to make sure the parts are self-extinguishing, and we don't want to fire up there. So, but given that there are fires, we want to make sure if there's fires that are accessible, you can fight them. Like if an oven catches fire in the galley, there's an extinguisher there, you can put that fire out. Nowadays, the big thing is batteries and iPads and phones that's all of a sudden just extinguished. All the airlines have bags that they can throw this in to prevent the fire from escaping. They've got gloves. They're trained to deal with these emergencies now, which was never an issue until the last 10 years maybe. But laptops, iPads, phones, they can all get damaged or just suddenly go into a fire. So you can't just fight that with an extinguisher. There are certain protocols for fighting lithium-ion battery fires on board. But we've got to hope that there's no fires that are going to happen inside the cabin under a normal circumstance. And we're trying to look at all the scenarios that could happen. And we're going to talk about the Swissair, because that really made a big mark on some of the tests we have to do now in the hidden areas. And we'll talk about that in a bit. But yeah, the requirements were established based on full-scale testing. Okay? So I don't think we're not worried about a fire we're at altitude. It's either in-flight fires will get self-extinguished, or on the ground we provide an area, a cocoon of passenger area that we can play people off the aircraft, knowing that there's going to be a fire and it's going to burn the plane up. At that point, we don't worry about the plane life. Radiant panel was introduced based on that Swissair accident to look at propagation of fires in hidden areas of the aircraft. So this test was specifically came into play based on fires that were in the overhead area, particularly the thermal acoustic insulation. Burn through, so someone mentioned about how the fuselages. So this is the test that was developed to provide a barrier even more barrier for a fire outside the aircraft to penetrate in. And so the insulation that all the aircraft have in that area wasn't really well defined as far as to help us. So now all the manufacturers have to prove that the insulation will actually act as a barrier. The aluminum on a normal aircraft will burn through very quickly. But this barrier of the insulation provides some more time to prevent the fire from coming inside the cabin. And they did do the same test with the graphite as well. That doesn't burn through as quickly as aluminum, but they still needed to determine that the fire would not penetrate through a graphite skin. And if you look at the pictures after the A350 accident, the fuselage is still intact. You can see the graphite strands in there, but I think the fire did get hold inside the cabin eventually, but the main fuselage did its job, I think, for the most part. Lessons learned. So there's actually a database that you can go onto that actually has a big matrix of all accidents, of aircraft accidents, and not just flammability, but they could be structural failures, but they're all listed in this particular index. So anyone can look at this. What I'm going to show here is some accidents that have occurred and actually created rules and new tests. So the first one, back in 80, there was, and I'm not going to read all this, you can look at it yourself. Essentially, there was a L-1011 Saudi Arabia. It was a full aircraft. They received a smoke indication in the cargo compartment. They tried to fight. I guess they tried to fight the fire because it had come through the floor. But when it landed back at Riyadh, the captain didn't elect to do an evacuation. And everyone on board that plane perished. And they don't know why they didn't ask for an evacuation, but everyone on board the aircraft perished. That was the aftermath of that. But what that did is it introduced new rules for cargo bay to prevent fires from coming through the cargo liner. So that was the start of this reactionary trend, I guess, to develop new tests. That's when before that it was just a Bunsen burner test, I believe. So the cargo liners need to have a much higher rating because they're non-accessible in flight. This next one, back in 85, is introduced so many new rules. I don't know if anyone remembers this. There's a British Airways, or British Air Tours 737-200. Never actually left the ground. He actually started off down the runway. The left-hand engine, one of the combustion cannons around the periphery, there was a bad weld. It let go, and it popped out through the side cowl and actually entered into one of the wing access doors. So this hot unit went in there. We had a fire. The engine was on fire. The captain knew there was a problem. I don't think he could see back there. So he slowed the plane down. He put the thrust reversers on. I don't know if you're familiar on the old 737-200s. The thrust reversers are the clamshell type. And as they open up, they're not vertical, they're actually angled. And actually that act, the fact he turned off the runway into the wind, all the flames were being blown by the engine and by the wind onto the back of the aircraft, rendering the back of the aircraft not possible to escape. They couldn't open the doors. It was not a good whole thing. Everything happened wrong. The materials inside the aircraft with the polyurethane foam cushions, all of the materials used for the fiberglass, for the bins, the ceilings, and everything we just talked about, were using an epoxy resin, which was, back in those days, that's what was used. It's a good resin, it's a good system, but it burns horribly, and it smokes hard. So this particular test, there were fatalities, there was exits that the slides disintegrated from the heat. There was no access around the door for people to assist. So this accident alone brought in heat release, smoke, seat cushion testing, the low-level lighting that you see on aircraft nowadays, assist space around exit areas, and hardened escape slides. There was so much that came out of this one accident, and it never left the ground. The plane was on the ground the whole time. That was the interior afterwards. And it really proved what these materials could do. And that wasn't even in the air. The back end of the aircraft fell down because of the heat that was coming back from that one engine. And I think there's a picture. So there you can see that clamshell on that on the thrust reverser, and how he just directed all the hot flames directly onto the back of the aircraft. So obviously most of the fatalities were back in that area. I forget how many, does it say how many fatalities?
Did it ever come out why he did that?
He wasn't aware that what was happening behind him. He didn't know that. He knew there was a problem with the engine, but he had no idea that it penetrated the wing tanks. He didn't know that putting the thrust reversers on was going to create more of a problem. I mean, it was just a bad series of events that occurred. Yes.
So from a regulatory point of view, it's a UK-operated carrier in London. Did this get over to the FAA? How did that?
Oh yeah, because the CAA, the equivalent in Britain, obviously it's an American aircraft, so the FAA had to get involved because it's a Boeing aircraft. So it was they definitely worked together with the FAA for sure as to what the cause was, and it came down to a bad weld. It was a repair station that didn't weld these combustor cans correctly.
Yeah, I guess my question was more about how the FAA, then they changed their testing requirements after that, based on the data from.
It sounds like the link was Boeing, though, not.
Yeah, it was because it was a US plane that was involved with this. That's how the FAA got involved with it. Although you're right, it was in Manchester, England, and it was a British operator, but it was a Boeing aircraft, and that's how that pulled the FAA into it automatically, and Boeing, of course. But yeah, and the FAA has a much better, had a much larger infrastructure to look at the testing. The CAA, in comparison, doesn't have that sort of resource. So the FAA definitely was a major help to get this thing looked at and investigated and determining what they could do. Anyway, there was bad. It really was bad. I think I didn't see how many people were killed. Sorry?
55.
Oh, did I say? Oh, no, okay. So like I say, these are the rules that were introduced. Areas around the exits, escape path lighting, heat release for large surfaces, smoke density for large surfaces, and seat cushion fire blocking. So there was a lot of scrambling being done at that time. And so what that did is, back in 1989, the FAA introduced rules to limit the amount of heat that was being generated off panels, and that made us change the resin on the interior materials from an epoxy resin to a phenolic resin. And that was the big change. Phenolic has a very low heat release and smoke output. It's not as strong as an epoxy resin, so it meant we had to put more layers of fiberglass maybe on the walls to provide the same strength on bins and bulkheads and so on. But that was the big change that was made, change from epoxy to phenolic on the interior. They still use epoxies, like I said, on the exterior, but because that's not meant to be self-extinguishing. These are, and that material is really good. We're going to come to the Swiss Air accident back in '98. So I don't know if you're familiar with this. MD-11 took off out of New York on its way to Switzerland, and it had something happen. The pilots had no idea what was going on. They were losing electrics, they were losing control, but they didn't appreciate what was going on. And it was because there was and it came down, there was a bad wire that had been installed by a company in LA. They did an IFE installation, in-flight entertainment installation, under an STC. They used the wrong wire and they bent it too sharp, and it arced, and that set fire to the insulation that was around it. And that insulation, although it was tested for just a Bunsen burner test, what no one appreciated is that so let's step back. The insulation on the aircraft, on the interior of the aircraft, it's a 1-inch batt, normally 1-inch batt of fiberglass, which that's not going to burn, but they cover it to prevent moisture ingress with a very thin mylar film. and it's either stitched or welded seamed around to prevent moisture from just filling up and making the plane so heavy with water. So that there's a reason for that mylar covering. The mylar that Douglas used was not as good as the one that Boeing used. The Douglas one, when you set fire under these conditions, the flame just spread. And that's what happened in the aircraft. It started in the flight deck, and basically all the installation above the flight deck and going backwards, the fire just spread along it. Then obviously it got wiring involved, and it got the ducting. It got into the air conditioning ducts, spread the fire further along. Yes?
This is a while back, so my information may not be right, or it was right at the time. I might be relating it wrong. But is it true that when they did the mylar that they were using, it was flame tested?
It was.
But when they did the test, it was not stretched. It was just loose, and the test it just basically shriveled up and went away. It didn't support any flame, and there was no noxious. But then when it was stretched, when it could not contract into a ball of nothing, then it actually emitted flame.
I think that's a true statement. The Bunsen burner test, if you put a Bunsen burner, it'll melt away from the flame temperature and then stop. And maybe it's but when you have it in a horizontal situation with a heat source as well, a radiant heat source from the fire, then it'll just expand along. If you do a test of that without a heat source, the material will probably pass. But in the aircraft interior, we had fire going on, and that just helped propagate that material. Douglas had to change all of their MD-11s as they were then, DC-10s, DC-9s were still flying, MD-80s, that's the whole series. Boeing's material was better. It met the new requirements, but nevertheless, everyone upped the ante, and although it was an AD for Douglas aircraft, it wasn't an AD for Boeing, but they still did a whole program to replace their interior insulation also, the mylar side of it anyway. So that was a huge thing. There's a very good documentary on how they determined what the root cause was of this. I forget what the one of these aircraft accident documentaries. This is the investigation into this, and they pulled the aircraft up from the seafloor and rebuilt it in Canada, and that's when they determined where that problem was. Crazy how they found it, but had the pilots known there was a problem, they had enough time to turn around and get back, but they had no idea what was going on. They were trying to determine why are we losing the system. They didn't appreciate what the problem was and how serious it was, because they couldn't see anything. There was no visual because it's all above the floor, above the ceiling. Anyway, it was bad, unfortunately, but it did make all of the insulation is now way more stringent. And we're also working on the wire test. We have a wire test that all the wires have to meet now with a Bunsen burner, but the plan is to actually to test with a radiant heat source to make it a much higher level. Yes.
How does teftel rate with in your wire test?
That's a wire, right? It's the insulation. I don't know. I'll be honest with you.
That's what we're all using.
I can imagine that if it's on the aircraft now, then that must meet a standard. There was PVC wire was the one that was bad. Yeah, I think the capsule is actually good. So that accident unfortunately brought in the acoustic insulation materials, and we're looking at the ducting and the wiring. So what that has done over the years has actually created a much more fire-hardened interior, providing this precious time. And I'm going to now show a couple of slides where this has proven well. So this is 2008. We had a 737 took off from Denver on a very strong crosswind, and it veered and actually crashed off to the side of the runway. Fuels broke up, major fire. Everyone aboard escaped. So that was the aftermath of that 737. Looks in a way similar to the Manchester one. You can see the fuselage is burnt through. But everyone got off that plane, and it was attributed.
It took longer to get in that condition than the previous photo we saw.
Of the Manchester one?
Get burned out like that. Then.
Probably, I don't know how. I mean, they just let the fire burn. They get people off the plane. I mean, they'll extinguish it, but I don't know how long it took to actually extinguish that after it was.
Or you're saying that egress was faster?
Yes. Well, I'm saying that the interior held up and provided valuable more minutes to get off that plane before it did burn. I mean, the interior did burn. I don't know if I got an interior. Yeah, I mean, the interior did burn. You can see some of the seats there. We're not going to stop the interior from burning, but if we can provide some more time, precious time to get people off that plane, then that's what we're about. We're not worried about saving the fuselage. It's gone at that point. The safety of life is what we're interested in. 2005, Toronto, an A340 didn't stop at the end of the runway, ran off over the ravine, caught fire. Once again, 12 people injured only. Everyone got off that plane. So that was the aftermath of that one. So once again, the plane burned, but everyone got off that plane successfully. And then the last, I haven't got anything on the 350. I guess I have to update my slides. But the Asiana flight 777 in 2013, when it landed short of the runway and broke up. Obviously, there was an in-flight. There was a post-crash fire. I think there were 3 fatalities. One of which was a fire truck hit. Yeah, which is unfortunate, and 2 other girls. But in essence, I mean, this was a survivable accident, as we call it, but there was a fire on board. Everyone got off that plane. You can see one of the slides is deflated there. I'm not sure why that happened. The other one just before the wing looks to be okay still, but it definitely burnt up. There was obviously impact from this, so the seats, you can see, definitely had some structural issues, but it was survivable. That's what and if it's survivable, we're going to get people off that plane. That was, I think, the forward section where a lot of that, you could see it burn through the ceiling. So we can't stop the plane from burning up. That's not the intent. We want to make sure that we can provide that precious time to get people off the plane. Yes?
How much of a weight penalty do we assume with the new materials to meet the new requirements?
I don't think there was a lot of weight difference, to be honest. Like I said, they had to put some extra plies on with the phenolic resins, but overall they've come up with different lighter weight coverings. They can use less dense core inside the honeycomb. I don't think it made a huge, I could be wrong, but I don't think it made a huge impact overall to the weight. Yes.
So in terms of the situation with the latest Coast Guard, post-earthquake crash in Japan, I guess the standard is to evacuate like 90 seconds or something. It was 18 minutes till the passengers were fully evacuated out of that plane. With an active fire. That seems to be almost ridiculous in terms of making it survivable that long.
It is, and that was, well, I'm saying it's because of the new materials that we're using on the interior. The 90-second rule is required by the FAA and any authority to demonstrate that you can get all the people off a plane. Now, that's not including the fire. That's just saying that some of the exits are blocked. You use people that supposedly have no knowledge of getting off a plane, although nowadays it's very hard to find people that have never flown, but they do have to demonstrate, and the 90-second rule is an FAA requirement. Our thought was if we can provide 5 minutes of time, then it exceeds that 90 seconds and get people off. We were fortunate that everyone got off in 18 minutes. I think there were some factors in there. They lost the communications. They had to use bullhorns. And if you probably saw the videos, people were still sitting in their seats with the smoke on. But that's, I think, more of a cultural thing, the Japanese, and I'm not trying to wait for instructions. No one took their carry-ons. I think that's a huge factor. But it still took 18 minutes because they only had 3 exits as well. I think there was the 2 at the front and 1 more. The ones at the back, obviously the fire was at the back of the aircraft again, so they knew they couldn't use the rear exits. But so it was a reduced number of exits. I think that's a great testament of how we've made these interiors better now. Because some of the photographs made it look like the whole aircraft was on fire. How could anyone get off that plane? But they were taken after the plane. Everyone had got off that plane. Everyone got off safely, which is a great thing.
We were told in my world, the commercial world, 15 minutes of an uncontained fire, 15 minutes, if you're not on the ground, the plane's done. Is there any documentation that supports that idea? Swiss Air is the one that kind of came up with that, where they said, we get a fire, we can't stop it, 15 minutes, no airplane's ever lasted longer than that. Does that sound right?
Well, that plane lasted an hour and 13 minutes before it actually hit the ground. So I think there's longer than 15 minutes. I think that's a very conservative number. If you're over the ocean, then you're not going to have. but that doesn't sound like a very long time. 15 minutes. I guess it depends on the severity, where it is, what it's affecting, what controls or systems have been affected. But
my guess is if it starts in the tail, you've got a little more time.
I would think so. It takes a lot longer to come forward from there, but yeah.
That Swiss Air too, and the unrelated electrical failure, hair on the back of your neck standing up that they ignored, sort of.
Yeah.
You know, that was interesting. Okay.
Right. So, sorry, you.
So in the Asiana one, I remember I had just landed at San Francisco. My wife and I were leaving the airport, and this big plume of smoke came up from the airport. And so we had just landed shortly before the crash. And I thought that there seemed to be a lot of fire from that to make such a big plume. How much fire was there? How did it fare in terms of evacuating people?
Everyone got off that plane as well. I mean, and even though it broke up to some degree, because the fuselage broke away from the wings, which may have helped it because there was no fuel immediately there. There was fire around it, but it's hard to say how long the fire actually lasted. Sorry?
Firefighters did a really nice job in San Fran.
I think they did. They got there very quickly and took care of business. And the fuselage did burn up, though, as you saw. I mean, there was obviously fire. Because once you get this, we call it a pool fire. You know, the pool of fuel on the ground, it's just going to burn until it burns out. So, and it takes a lot to get kerosene to burn. On an engine, on a diesel engine or a jet engine, we have to atomize the fuel, mix it into small droplets, and then mix it with air to make it burn. If you get some diesel and put it in a pan, you try and burn it, it takes forever to get that thing. You have to get so hot. Diesel on its own or kerosene doesn't burn that easily, but once it's going, then it's off. All of the burners that we use for the big tests, we use jet fuel to simulate what would happen. And are you okay to carry on? Sorry.
From a home builder's perspective, what materials short list would we want to have versus what would we want to avoid?
So that's a good question. Obviously, the plastics would be probably the worst. We already talked about wire. I think the wire you use on home built is fine, and there's not enough wire that would create a problem. But the plastics you used, someone mentioned about the fabrics on the seats, the seat cushions. I would recommend you go to a pretty good source like Aircraft Spruce, somewhere that has the materials that are certified to be used, as opposed to going and getting some foam from the local hardware store, because that is probably never going to. And the chances of you having a fire on board the aircraft, I think, is pretty remote. The other thing is, with a small aircraft, there's only one or two people normally. You can get out of that plane pretty quickly, as opposed to us trying to get 300 people off a plane. The rules are so different. Another example is, these executive 737s or even 747s, they have so few passengers on board the aircraft. The 90-second rule it goes away, because you can get everyone off that plane probably in 30 seconds if you really tried. So there's different rules depending on the configuration. But we deal mainly with the passenger aircraft. So. But in answer to your question, as long as you don't have, I don't believe you have to test if you change the materials, but it's very easy for us to run a test and make sure it isn't going to just explode into flames. I mean, But it's mainly the plastics that you got to worry about, I think. Plastics and the seat cushion.
Stuff like sheepskin, seat covers.
So on the aircraft, the pilots, and normally have a sheepskin. They're all treated. I mean, they have to meet the same tests as the passenger. We don't make exceptions for the flight crew.
You see a lot of sheep running around on fire, though. So.
And I burnt cows, and that's interesting. It smells terrible when you burn leather. It really does. I'm sure the same with sheepskin, but they get treated. There's treatments that different people do particularly for commercial aircraft. Before they can go on an aircraft, they have to be tested. Nothing can get on an aircraft without having some tests done and part of either the TC on a new aircraft or an STC. So that's what most of my business is. So I want to show you the videos. I'll run through this quickly. That's a typical Bunsen burner cabinet that we build. We measure the flame height so it's consistent. The tip of that is 1700 degrees Fahrenheit. It's a pretty hot flame, even for a Bunsen burner. And I believe this is one of those tests. So we bring the Bunsen burner in. I think this is a 12-second test. It's just there for 12 seconds.
What's being tested?
Looks like a thin panel. That's what we want to happen. We want it to go right out, just like that. That's a good one. So this one here, this is a piece of foam, I think. So I remember. Once again, 12 seconds Bunsen burner vertical test. So we can see here the flame has not self-extinguished, and it'll start once it starts. So we've already failed because it's gone beyond 15 seconds, and it's starting to drip. Whether the drips are long enough, they are self-extinguishing as far as I can see, so that's not a problem. But it failed because it didn't self-extinguish. All right, let's move on. This is a horizontal test, which we use for elastomers. So we have to test everything on the aircraft, but some materials will never meet the 60-second or 12-second vertical test, but we need to test in some fashion. Acrylics that we see, because they have a good see-through properties, they'll never meet the vertical test. They'll drip, but they need to be no propagation. So we have to test with this test. So you can see a very slow propagation here on this. And we measure it with a timer to see how far it progresses. And like I say, it's 2.5 inches a minute. So it's 10 inches in 4 minutes. I think I misread that earlier. All right, we'll move on. The wire insulation. So this is the wire test. We string the wire up at a 60-degree angle. We apply the same Bunsen burner to it, and it has to be self-extinguishing. Of course, it's not the wire that's going to burn, it's the insulation, of course, which I'm sure you all understand. So I think this is a wire test. Oops, no. There we go. The flame's a little higher on this, but still the same temperature. And you can see the insulation just chars. It doesn't burn. The biggest problem we have is very thin wire. Someone mentioned 28 gauge. We have to put weight on to keep it taut. And I've resorted to using a paper clip with a thin wire just to provide enough tension, but we don't want the wire to break, because it's not a failure, it's a void. Because the wire is not the problem. But
we hate 28 gauge.
Oh, yeah, you did too, don't worry.
There's no requirement, test requirement for the insulation to remain insulating for a certain period of time?
No, that's not. We don't test it afterwards. You just want to make sure it self-extinguishes. So this is the heat release test. I'll span through this. That's the control panel. That's the actual chamber. Basically, we have high voltage glow bars, high power glow bars that provide a lot of radiant heat. The air is introduced at the bottom of that chamber, runs through, and we insert a sample into there, and we ignite it, and we measure with thermocouples how much heat is being generated during the test. It's a 5-minute test. Minutes, I don't think. So there's a sample that's been inserted onto the holder. And the sample is an example. It's a 6x6 sample of exactly what a bulkhead would look like, a bin door, anything that has a large surface. So we have a lower pilot, and you can see the upper pilot. The sample gets injected. It starts to burn. And we measure the starting, I'll make it easy, the temperature to start with in the exhaust, and we watch how the temperature increases during the test, and we can determine how much heat is being generated from that. Sometimes the panels pop, that's something that happens. But that actually is a pass. It looks like it burns, but you can see it peaked, the front surface burnt off, and that's good. That would have been a pass. So. The panel doesn't really burn. It's the covering that typically burns on these things. This one, probably not so good. Yeah, that's probably a fail. Bow flames coming off that. Yeah. Once again, I'm not going to show the whole thing, because I want to try and get through this. Smoke. The smoke test is an old test that was determined many years ago by ASTM. It's a box of 3 by 3 by 2 foot. It's a sealed box. We put a 3 by 3 sample in there. We set fire to it with a radiant heat source, and we measure the smoke. We have a light source below, and we have a photometer on top, and we measure the collimated light source. When the light source is through, that's 100%, and we adjust to give you 100% on the computer. Then we put a shutter in the way to simulate that chamber is black. You can't even see through it. And so we have a range between very good and very bad. When we run the test, we're monitoring that signal, and we can determine how much smoke is being generated by that sample during the test. Let me come down. So there's the setup. It's got a video on that. I didn't know that. So you can see that's the furnace there in the middle. There's the light source coming through a lens system, and it goes up to an upper window, and above that is where the photometer is. These rods hold everything in place very securely, so there's no change. We measured the thermocouple of the surface of the chamber. You can see the furnace there, and then the sample is here. And it gets introduced, and there's some pilots to actually make the unit burn. We want it to burn with a heated source, and then see what happens. Flame propagation. So this has got some good. There's the heater that we apply, a radiant heat source. I'll just run through these quickly. So this is an insulation. That's the yellow is a mylar material. It's going into the chamber. We drop a pilot to try and induce a flame. And lo and behold, it supplies for 15 seconds. You can see there's absolutely no propagation. This is a good material. We're only allowed 2 inches of propagation and no after flame. So that's a good test. This one here. So this was not so good. We were actually getting propagation. You can see the flame moving along. So that actually was a failure. That would not be allowed to go on an aircraft. And then I had this material was presented to us as insulation inside an oven, which also had to meet its insulation. And this was a lab actually just down the road from here in Stanwood. And
this is for an oven?
It's
an aircraft?
Yeah, it was an aircraft oven. They wanted to put this inside the oven of an aircraft. Obviously, we told them no, this is not working. We had to get the extinguisher to put that out. That was horrible. That was.
You kind of co-opted a question I had, which was, now that all these new standards have been established, haven't most of the people submitting samples meet those standards?
There's always new ideas. There's always new materials. People come up with different, and if it's different colors, we have to establish, does the color make a difference? The pigment. I mean,
Pigment good.
yeah. So we do have to keep on testing. So this one, we talked about the seat test. So this is you can see this has got a seat cushion base and a back. The burner, sorry, was set for warmed up for 2 minutes.
Looks as comfortable as the chairs in the...
Yeah.
Do they call that the hot seat?
Yeah, that's the hot seat. Below here is a scale. So the criteria for a seat cushion is you cannot lose more than 10% of the weight loss of the cushion. So we measure at the beginning and we measure at the end after the test. And that's how we determine whether a seat actually, the cushion, the foam is acceptable, and the dress cover.
Not making a lot of smoke.
It's not making a lot of smoke, but you can see how much flame is on that thing. And this test is 2 minutes like this. I'm actually going to drag this over, so I don't want to, it doesn't look much different there, but... Okay. So that's the end of the test. The burner goes out and we take it back to the home position. This test lab is actually in Recaro in Germany.
Now, was that more than 10% consumed?
That was probably 5%. It was this is a good test. Eventually it would go out on its own. We allowed another 3 minutes. If not, we extinguish it. But that passed easily. It was a good material. But you can see from the flame, we actually put a lot of heat onto that thing. So that's all seats have to meet that. So
you have an exhaust hood in there. Is there a difference in a sealed room versus an exhaust hood?
We need to have some ventilation, and then that is natural. We test actually with an anemometer to make sure the airflow. It's not normally sealed. There's some circulation that's allowed that we do set before we do the test. At the end of the test, we just turn it on to get rid of that smoke. But just very quickly, fire containment. So all of the trash containers on the aircraft have to be self-contained, that there's no fire will come out if there's a fire in a galley or a lav waste compartment. So we have to test those as well. Once again, every configuration is a little different. The flapper's different. I'm one of these people, when I go on an aircraft, I make sure I get a pad napkin, push it down and make sure that door closes, because I know how important that is. Passengers have no idea. They just cram it full, they leave the door open. That's not what is expected of those things. So be one of those people.
Place for sneaky people to hide their cigarette.
Well, and that's the thing. When I worked for Britannia Airways, we carried a lot of school kids on trips to Europe. And we were always concerned, because smoking was allowed on the plane then, that the kids would go in away from their teacher and have a cigarette inside the lab. And if someone bangs on the door, what are they going to do? They're going to just throw it in and so we were really concerned. In fact, we put smoke detectors on our aircraft before it was a rule, because we were really concerned what was going to happen inside a lab. So anyway. So basically we build, or the customer builds to production standards, a unit. These are just some pictures. The waste bin goes in there. And then we set fire. We fill it 2/3 up with materials. We make sure it's burning well. There's thermocouples inside to measure. That's what you can see there. We close the door and we monitor it, and we look for. We actually introduce gaps. There's little tabs on around the door. We actually put as though the door is not closed properly. So we try to introduce some air into the unit. Oh, what happened there? What happened? So that's actually part of the test. You can see it's smoking. This one actually, with the waste compartment, you can see it didn't do anything. Now we take the waste compartment out, because if you want a plane to fly and you've lost that waste compartment, that's an MEL. You can't fly that plane unless you know that it's going to meet the requirements. So we do a test where we fill the compartment up totally with trash, and there's paper cups, tissues. There's actually, the FAA has a list, and we have to meet the final. We have to test them all. They have to be conditioned, and then fill it up. And so there's what's lighting this one. This is a bit more tricky because now we have to go through the top, and we have to watch to make sure. My job as a witnesser is to make sure that that thing is burning well before we close the door.
Pictures.
And we evacuate the room. No. I had one that took almost 2 hours before it went out. But we have to wait.
Had such a small amount of oxygen getting in.
It was just a large volume, and it just took forever. What happened was, it would go out, and then an ember would drop down onto the next level and start up again. And so we're monitoring this with thermocouples, and that's our rule. We have to come down to 150 degrees to say it's gone out.
So, question.
Yeah.
So the first thing that's going to happen now is somebody's going to smell smoke.
Yep.
And
hopefully they're going to fight the fire, right? I agree with you. So, but we still have to go through this test until the conclusion, I guess. This one, we couldn't be in the same room. It actually got to the point where we couldn't actually see the test.
Did that one pass?
It did, because it contained the fire. And let's move on. So that's after the test. You can see it's all burnt around, but it contained the fire. There was no fire escaping. And that's what was left of the inside after we finished. So that was the inside the doors. It contained the fire, though. Anyway, so that was a little addition. That's one of the jobs that I do, is to witness all these tests. So it's a fun job. I set fire to things.
What about the toxicity side of this? Are you just involved in the
So we do the toxicity. We make equipment to measure the toxicity too. So, but
that as part of this test or a separate test?
It's part of the smoke test. We don't do it on the fire containment. The smoke chamber, at the end of that smoke test, is when we extract the gas and analyze it for the different gases that can cause problems, the hydrogen cyanides and so on. So yeah, so we get involved with that as well, but it's not an FAA requirement. I don't have to witness those tests, but I teach people how to do it. So that's part of my job. Okay, any other questions? I'm sorry it went on longer than planned, but...
Appreciate it.
Oh yeah.